This is section 3.7, Limiting Reactants, our final section of chapter 3. There are two topics that are covered in this section. The first one is the issue of limiting reactants. The second one is a brief introduction to types of chemical reactions. When you move on to the next course, Chem 1100, you'll look at more detail in types of chemical reactions, but this is an introductory discussion of that. But the main focus of this section is limiting reactants. And again, it can be sometimes misleading, the number of pages in a science textbook that are dedicated to particular topics. This topic right here is a relatively advanced topic compared to some of the earlier ones, certainly the ones in chapter 1 or 2. So even though there's only a few pages dedicated to limiting reactants, it's an important topic that requires some real thinking. So here's the issue. In section 3.6, we looked at stoichiometry, we looked at amounts of reactants and products. Now we're going to look at a specific case of amounts of reactants and products. The case where we don't match up perfectly the amounts of the reactants, meaning we have more of one reactant than of another, and that affects how much of the product we're going to get. So many analogies are used out there. An example would be sandwiches. If you have a loaf of bread, but you only have 3 slices of bologna or 3 slices of cheese, you realize that you probably wouldn't be able to use the entire loaf of bread to make sandwiches because the bologna or the cheese is limiting how much of the bread you would use. Likewise, if you had 20 packages of cheese but only 2 slices of bread, the number of sandwiches you could make would be limited by the amount of bread that you have. We call that the limiting reactant. And you can think of the reactants here almost like ingredients in baking a cake or cupcakes or cookies. Really, that is chemistry. When you bake something, you're really running a chemical reaction, a complex set of chemical reactions. And the amounts of materials that you're putting in affect how much of the products you're getting out. So if I have 30 pounds of flour, I can make a lot of cake. But if I only have a half a cup of flour, I can only make a little bit of cake. So let's take a look at an example here. Here's some terminology first. The limiting reactant. The reactant that is used up first in a reaction is called the limiting reactant, meaning that there's only enough of that reactant to make a certain amount of product. But you can have another reactant where you have more of it, and that's called the excess reactant. So the excess reactant is that it's the material that's present in quantities greater than necessary to react with the quantity of limiting reactant. Okay? So you can take a look when you look at the ebook, look at the animation, a reaction between NO and NO2. I'm going to move on here to determining the limiting reactant. So take a look at the chemical equation here. CO gas plus 2H2 gas to form CH3OH liquid. Carbon monoxide gas plus hydrogen gas forms CH3OH liquid, which is methanol, liquid methanol. Okay, this is a reaction that can be run. Notice the stoichiometry. 1 mole of CO reacts with 2 moles of H2 to form 1 mole of CH3OH. It's a 1 to 2 to 1 ratio. So here's an example. Suppose that we initially have 5 moles of carbon monoxide, 8 moles of H2. Let's do a calculation of how much methanol we're going to make. And notice they draw little pictures down there, but you're going to be doing these sorts of calculations without the pictures. So that's just there to show you what it would look like physically. Remember, in chemistry, we're using equations, the balanced equation, to visualize what's actually happening. And that's an abstract thing, but it's something we need to get good at. So what I'm going to do is I'm going to focus on the following idea. Suppose that we have 5 moles of CO. How many moles of CH3OH could we get? The ratio is 1 to 1. Every time 1 mole of CO reacts, you get 1 mole of CH3OH. Remember, there is no 1 in front of the chemical formulas. We don't put 1 in front of the formulas. So if there's no number in front of the formula, it is 1. So if 5 moles of CO react, you're going to get 5 moles of CH3OH. Think of it like a shoe. If you have 5 shoes, you need 5 shoelaces. It's a 1-to-1 ratio, 1 lace for every shoe. On the other hand, what about the H2? We have to take that into account as well. There are 8 moles of H2, and the ratio is 1 mole of CH3OH for every 2 moles. So every time you put in 2, you get 1 out, half as much. So if we put in 8 moles of H2, we get half as much of methanol out. We get 4. 1/2 of 8 is 4. So now we have an interesting relationship here. What it tells us is that if we put 5 moles of CO in, we'll get 5 moles of CH3OH. However, if we put 8 moles of H2 in, we only get 4 moles of CH3OH. So the question is, if we have 5 and 4, what are we going to get as our options? Which one is going to be the correct one? And it's the smaller of the two. If CO can form 5, but H2 can only form 4, we're only going to get 4 out. So look at the picture there. See what happened? We get 4. We get the smaller of the two. We also have some CO left over, right? Because CO said we could get 5. So some of the CO is not going to react. It's going to be left over. That's called the excess reactant. So CO is the excess reactant. Okay. Now, if you take a look here, they go through a calculation of figuring out essentially how much of the CO is going to be left over. So what they do is they say, look, the moles of H2 that we would need to react with CO is done in the following way. We have 5 moles of CO. In the balanced equation, we need 2 moles of H2 for every 1 mole of CO. So the moles of H2 that we would need to react with the CO would be 5 times 2 over 1. And that would give us 10. But we only have 8. So now what we would do is we would say that we're going to have extra CO and not enough H2. So take a look here at the bottom of this. It says, thus there will be 4 moles of CO consumed and 1 mole left over. We're going to have some CO left over. Okay. So let's take a look at an example. This is sample problem 3.12. Alka-Seltzer tablets contain aspirin, sodium bicarbonate, and citric acid. Okay, so there's 3 substances in there, but in terms of the fizzing, we're only considering 2 of those reactants. We're not going to focus on the aspirin. When they come into contact with water, the sodium bicarbonate and the citric acid react. So they need water in order to react. Generally, solids don't react with each other unless they're in contact with water. They react to form carbon dioxide gas, among other products. Okay, so here's the balanced equation. 3 sodium bicarbonates, 3 NaHCO3, reacts with 1 citric acid, H3C6H5O7. There are 3 products, 3 moles of carbon dioxide, 3 moles of water, and 1 mole of what's called sodium citrate. Now the question here is very specific, and one of the things that could be confusing about this problem is the formulas. The formulas are not simple. It's not H2 plus O2. It's some sodium in there, hydrogen, carbon, and oxygen. So you have to really focus on what substance we're talking about. The first reactant is sodium bicarbonate. The second reactant in the equation is citric acid. The formation of CO2 causes the trademark fizzing when the tablets are dropped into a glass of water. Alka-Seltzer tablet contains 1.700 grams of sodium bicarbonate and 1.000 grams of citric acid. Determine for a single tablet dissolved in water, A, which ingredient is the limiting reactant, B, what mass of the excess reactant is left over when the reaction is complete, and C, what mass of carbon dioxide forms. They don't ask us for how much water or sodium citrate is formed, just the carbon dioxide. Here, a little picture of the reaction. When you take Chem 11, you'll actually do this reaction in one of the laboratories later in the course. So here's our strategy. Convert each of the reactant masses into moles. So you're given masses, grams, 1.7 grams, 1.0 grams. You're going to convert those into moles by using the molar masses. Remember, back in section 3.4. Use the balanced equation to write the necessary stoichiometric conversion factor and determine which reactant is limiting. Again, using the balanced equation, write the stoichiometric conversion factors to determine the moles of excess reactant remaining and the number of moles of CO2 produced. Finally, use the appropriate molar masses to convert moles of excess reactant and moles of CO2 to grams. So once you got the moles of CO2 formed, use its molar mass to get the number of grams. Okay? So they wrote here out the molar masses. They tell you that sodium bicarbonate has a molar mass of 84.01. Citric acid is 192.12, and carbon dioxide is 44.01. It's nice to have that information organized. Then they tell you the stoichiometric ratios, the conversion factors. 3 moles of sodium bicarbonate per 1 mole of citric acid. Remember, that's coming from the balanced equation. 1 mole of citric acid for 3 moles of sodium bicarbonate. That's just the reciprocal of what we saw on the left. Then, since we're interested in carbon dioxide, 3 moles of CO2 for every 1 mole of sodium bicarbonate, and 3 moles of carbon dioxide for every 1 mole of citric acid, just so that we have all of those. Notice the moles of CO2 is on the top in both of those cases, and that's because we're trying to find the mass of them. So we're trying to find out how much CO2 we have, so they'll be on the top. CO2 will be on the top, that is. Solution. So first step, convert the amounts of reactants into moles. So you have 1.700 grams of sodium bicarbonate. Dividing by its molar mass gives you the moles of sodium bicarbonate. You have the number of grams of citric acid, 1.000 grams. Divide that by its molar mass. That will give you the moles of citric acid. How do we figure out which reactant is limiting? Well, one way to do that is to say if we take the moles of sodium bicarbonate, 0.02024, and we figure out how many moles of citric acid are needed to react with it completely, it would be a third because there's 3 moles of sodium bicarbonate for every 1 mole of citric acid in the balanced equation. So if you multiply that, 0.02024 by 1/3, you find that you need 0.006745 moles of citric acid to completely react with the sodium bicarbonate. We don't have that amount though. We only have 0.005205. That means there's not enough citric acid to react fully with the sodium bicarbonate. We would need 0.006745 moles of citric acid to react completely. We don't have that amount. We have fewer. So that means that the citric acid is the limiting reactant. And if citric acid is the limiting reactant, the other one, the sodium bicarbonate, has to be the excess reactant. So now we know which one's limiting, citric acid. That will determine how much of the product we get, of every product. Once you determine the limiting reactant, that's the number you're going to use to figure out the amount of the products. So 0.005205 moles of citric acid. Okay. And now, I'm sorry, it's jumping ahead here. Let me go ahead. To determine the mass of excess reactant, I went a little out of order. To determine the mass of excess reactant left over, first calculate the amount of sodium bicarbonate that will react. So limiting reactant citric acid, 0.005205 moles. 3 moles of sodium bicarbonate will react with it, so you multiply it by 3. So that tells you how much sodium bicarbonate will be consumed. 0.01562 moles of sodium bicarbonate. So now, how much sodium bicarbonate did we start with? 0.02024. How much will react? 0.01562. Well, the amount that you start with minus the amount that reacts is the amount that's going to be left over. So that would be 0.02024 minus 0.01562. and that would be 0.00462 moles. They don't show that calculation, they just give you the answer, 0.00462 moles unreacted. Now, we want to know how many grams that is. Well, multiply it by the molar mass of sodium bicarbonate, 84.01 grams per mole. That will give you 0.388 grams. So that means 0.388 grams of sodium bicarbonate will be left over. Part B is done. Part C, to determine the mass of CO2 produced. Now, what we can do is we can say again, the limiting reactant is citric acid. We know that 0.005205 moles of citric acid are going to react because it's the limiting reactant. Multiply that by the stoichiometric ratio. I'm coming back up here. 3 moles of CO2, that's on the far right. 3 moles of CO2 per 1 mole of citric acid. Where did that come from? That came from the balanced equation. So if we multiply 3 over 1 times that 0.005205 moles, we get 0.01562 moles of CO2. Multiplying that by its molar mass, 44.01 grams per mole, that will tell us the number of grams of CO2 that's produced, 0.6874 grams. And there we go. We've got our answer. 3 things we did there. We figured out which one was the limiting reactant, citric acid. We figured out how much sodium bicarbonate was remaining unreacted, 0.388 grams. And we figured out how much CO2 was produced, 0.6874 grams. Those are the 3 things that really you need to be able to do in this sort of calculation. So practice those. You need to be able to figure out which one's limiting, which one's excess, how much of the excess reactant is left over, and then how much of the products you're going to get. Those are essentially the calculations we do here. So try the practice problems. And now, moving up here to reaction yield. Reaction yield is essentially an experimental issue. If we do the experiment, we may get a different answer. And the reason for that is when we run a reaction, sometimes we lose some of our reactants, sometimes we lose some of our products. It could get stuck on the container, or maybe things don't react completely like we hoped that they would. So then we have to do what's called a reaction yield calculation. The calculation you just did in that problem, in sample problem 3.12, that calculation of the amount of CO2 we got, that's called the theoretical yield. The theoretical yield is the calculated amount of the product that we get in the reaction. However, we might get less than that. So here's an example. Aspirin can be synthesized through the reaction of salicylic acid and acetic anhydride. So here's the reaction shown. Very simple stoichiometry, 1 mole of each reactant, 1 mole of each product. So in this particular problem, 104.8 grams of salicylic acid reacts with 110.9 grams of acetic anhydride. Calculate the percent yield if the reaction, if 105.6 grams of aspirin is produced. Now be careful here because she calls it percent yield, but it's also called reaction yield. Reaction yield or percent yield are the terms that are used. Look at the formula here, equation 3.2. Reaction yield or percent yield is the actual yield divided by the theoretical yield times 100%. Okay? Again, the theoretical yield is what you calculate. The actual yield is what you determine experimentally. So if you calculate 6 grams of product, but you measure it and you only get 5, you would take 5 grams over 6 grams and multiply that by 100 to get a percent yield or reaction yield. So in this problem, really what they're having you do is the theoretical yield calculation and then the percent yield calculation. So I'm not going to go through it. The actual calculation is relatively simple. What you do is you figure out which reactant is limiting. Once you figure out which reactant is limiting, you calculate the mass of the product you're going to get out of that, and that would give you the theoretical yield. So in this example, they figure out that since everything's 1-to-1, the salicylic acid is the limiting reactant. If you take a look, the amount of salicylic acid that you have is 0.7588 moles. The amount of the other reactant, which is acetic anhydride, is 1.086 moles. So since it's smaller for salicylic acid, that's the limiting reactant. So once you figured out that the limiting reactant is 0.7588 moles, you can calculate how many moles of aspirin you're going to get because it's a 1-to-1 ratio, so that would be 0.7588 moles. Multiply that by the molar mass of aspirin, and that gives you the grams, which is the theoretical yield. Now, it tells you in the problem that the actual yield is 105.6 grams of aspirin, not 136.7. So to find the percent yield, you take the mass that you actually produce, 105.6 grams, divide that by the theoretical yield, 136.7 grams, and multiply that ratio by 100, and we find that it's 77.25% yield. Okay? So you can try those as well. There is a little short discussion here of types of chemical reactions. There are what are called combination reactions. Read over that. Combination is where you take either elements or molecules and you combine them to form more complicated molecules. So NH3 plus HCl forms NH4Cl. That's a combination. You're taking smaller molecules and making a bigger one. Decomposition is essentially the opposite. You heat something, generally you have to heat them, and that will break up into smaller things. So for example, calcium carbonate, heat it and it will break up to calcium oxide and CO2. So something bigger forming something smaller, that's called a decomposition. It's essentially the opposite of a combination. Combustion is a very specific type of reaction. It's a hydrocarbon reacting with oxygen to form carbon dioxide and water. So if you see a hydrocarbon, something with hydrogen and carbon, reacting with oxygen to form CO2 and water, that is a combustion reaction. Okay? So the sample problem walks you through those different types of reactions. And so practice through those, practice your checkpoints. Again, the limiting reactant calculations are pretty complicated, so you want to practice as many of those as you can, and you will have essentially gotten through all of the topics in the course. So good luck with this, and I hope it goes well for you.